Go out and find a girl. Come on, we dance all night despite the heat. Okay, we're live. All right, so calorimetry. We've already talked about how we measure heat by measuring mass and changes in temperature using specific heat capacity. Let's look at our constant pressure calorimeter, or a coffee cup calorimeter, because when you do this in lab, you will be using just coffee cups. So, at constant pressure, the change in heat is equal to the change in enthalpy of our system. It's not quite energy, not quite internal energy, but it's close. Okay, so but the thing is, we're not measuring Q directly because we're not measuring the heat or the temperature of the reaction going on inside this calorimeter. We're measuring the temperature of the water. Okay. So the system is our reaction of some kind. The reaction takes place inside the water. We're not measuring the temperature of the reaction. We're measuring the temperature of the water. The water is the surroundings. Okay? And because, we have, a decent insulator in the styrofoam cup, we can sort of just kind of justify saying that the water represents all the surroundings that really matter. Okay. Remember, the system and the surroundings. The system is what you care about. The surroundings is literally everything else in the universe. Well, we're kind of cheating, and we're saying that the water is all of the surroundings. And on a short time scale, in the immediate, that's true. Okay. Technically, the heat of the reaction will diffuse out to the rest of the universe over time, but in the first minute, it's just having an effect on the water. So that's all you really need to measure. So it works. It's a decent cheat. Okay. Now, system is the reaction. The surroundings is equal to the water. Therefore, when we're measuring the system, we're doing so by measuring the surroundings. Okay. So Q of the system is equal to negative Q of the surroundings. So the Q of the reaction is equal to negative Q of the solution. The heat lost by the reaction is the heat gained by the water, or vice versa. So when we're measuring the heat of the reaction, it's negative mc delta T. So that's an important thing to remember. When the temperature of the water goes up, it's because the reaction is losing heat to the surroundings. Okay? If the temperature of the water goes down, it's because the reaction is sucking heat out of the surroundings. So if the temperature of the water goes up, it means it's an exothermic reaction. The reaction is losing energy into the surroundings. If the temperature of the water goes down, it's an endothermic reaction. The reaction is taking energy from the surroundings. Energy is going into the reaction. So that negative sign is really important. Okay, so when you're doing that calorimeter work, don't forget, Q of the reaction is negative Q of the solution. You're measuring the temperature of the water. You care about the temperature change, or you're measuring the heat change, I should say, of the water. But you care about the heat change of the reaction. Remember that negative sign. So, if you were to mix 50 milliliters of sodium hydroxide with 50 milliliters of hydrochloric acid, the solution temperature increases from 22 to 29-ish degrees Celsius. What is the heat released by the reaction, and what is the enthalpy of the reaction? Okay, those also, again, are not the same thing. Okay, so our 50 mils of sodium hydroxide and 50 mils of hydrochloric acid. Because they're solutions, they're not exactly 50 grams, but they're close. And we have the specific heat capacity of our solution, and we have the temperature change of our solution. So Q is equal to negative mc delta T. Okay? So Q of the reaction is negative mc delta T. Because we're measuring the water, we care about the reaction. So negative, the mass of our reaction is the mass of those two things combined because we added them together, and that was 49.9878, I think it was. Yes. Plus 50.0110 gets us not quite 100 grams, 99.9988 grams for a total mass of our solution, multiplied by the specific heat capacity, which I gave to you, 3.878 joules per gram degrees Celsius. It's not quite the specific heat capacity of water because it's not pure water. It has stuff dissolved in it. And then we multiply that by the change in temperature. It finished at 29.495 degrees Celsius, and it started at what? 22.120. 22.120 degrees Celsius. All right, so first up, we're going to have to do this. 29.495 minus 22.120. So this is 7.375 degrees Celsius. So the temperature of the water went up. Okay, so it's a positive change. So this is going to be an exothermic reaction. So we're going to get a negative value for Q. So now we can multiply these three numbers together. 99.9988 times 3.878 times 7.375. Q is equal to negative 446. So we're going to have four significant figures. 2860 joules of heat. Okay, so this reaction, this specific instance of the reaction, released 2,860 joules of heat. Okay, notice I'm specifying, this specific instance of the reaction. So this specific, this particular, this exact mixture released this exact amount of heat. But I also asked about the enthalpy of reaction. So delta H, enthalpy, represents the amount of energy sort of lost by the ideal sort of reaction. So instead of saying how much did this specific mixture lose, we're asking what is the enthalpy change for the reaction in general. Okay? So to do that, we have to divide by the number of moles that took part in this reaction. Okay? So we just pick one of them at random. It doesn't matter. They're both the same. And we have a 1 molar solution of sodium hydroxide. And we had 50 milliliters, so that's 0.05000 liters. So that means that we had 0.05000 moles of sodium hydroxide. So in order to get the enthalpy of reaction, delta H is equal to Q of the reaction divided by moles. Okay, so we have 0.05 moles, we have 2860 joules, so delta H is equal to negative 2860 dot joules divided by 0.05000 moles. So divided by 0.05 gets us 57.20. I'm going to go ahead, kilojoules per mole, negative 57.20. Again, be very careful with those signs. So that means that the neutralization of sodium hydroxide and hydrochloric acid, generally speaking, releases 57.20 kilojoules of energy per mole. Okay. It's actually slightly more complicated than that, because it's also, taking into account the coefficients of the reaction. But in this case, it's a 1-to-1 to 1-to-1 thing, so that makes it somewhat simpler. But that is an enthalpy of reaction problem, where you divide the heat released by a specific instance of the reaction by the number of moles involved in that reaction to find the more general expression, kilojoules per mole, for the reaction as a whole, rather than just this one instance of it. Now, a bomb calorimeter is similar to the coffee cup calorimeter. It's measuring the same sort of stuff, but it's constant volume. And not only that, but these things have to be specially made, because they have to be a very solid canister in order to withstand the changes of pressure going on inside them. Also, at constant volume, you're not measuring enthalpy, you are actually measuring the change in internal energy directly. But it's the similar sort of setup, because the heat of your reaction is still going to be negative heat of the water. And because these things are specially made, they always have a particular amount of water in them. They're very well calibrated. They're excellent pieces of equipment. So instead of being MC delta T, it's just C delta T. Okay. The calorimeter itself has a very well known, very well measured heat capacity. And it always uses a certain amount of water, and thus the heat capacity will always be, this value C. So we don't have to worry about mass for a bomb calorimeter. It's just C delta T. And that heat capacity is measured in joules per degree Celsius, not joules per gram degree Celsius. So how many calories are there in 10 grams of sugar? Okay. You burn 10 grams of sugar, and it raises the temperature of the water in your bomb calorimeter from 20 degrees Celsius to 25.182 degrees Celsius. And the heat capacity of this particular calorimeter is 30.046 kilojoules per degree Celsius. What is, not the enthalpy, this should be what is the energy change, the delta U, not or delta E in terms of the book, but what is the internal energy change for this reaction? All right, so 10 grams of sugar. We need the page. So Q of our reaction is negative C delta T. So it's going to be negative 30.046 joules per degree Celsius times our change in temperature, which it went from 20 to 25.182, so our change in temperature is just 5.182 degrees Celsius, final minus initial temperatures. So we multiply those two numbers together. Gives us negative 155.7 joules of heat released by this particular reaction. But the internal energy change, we're going to be doing the same sort of thing. We want to generalize it. So we need to know the number of moles of sugar that we burned. Well, 10 grams of sugar, and sugar has a molar mass of 180.156 grams per mole. So 10 divided by 180.156 gives us 0.05507 moles of sugar. So the more general form of this reaction, delta U of the reaction, is Q over N. So it's going to be negative 155.7 joules divided by 0.05507 moles. By 5507 is negative 2,805 joules per mole, or negative, that can't be right. Oh, yes, good thing I caught that. Okay, I was incautious. It's kilojoules per degree Celsius, so this is kilojoules. Okay. Yeah, because otherwise the answer would have been 2.8 kilojoules per mole, and that would have been wrong. 2,800 kilojoules per mole is much is right. That's the right size of the value. So yes, burning sugar is very, very exothermic. Okay. So that is how we do that. We can calculate enthalpies of reaction. We can calculate internal energy changes of reaction using different kinds of calorimeters. And you would, in an ordinary semester, absolutely, definitely do something like this. Well, not like this. You would do something like this in a coffee cup calorimeter. In this semester, I do not know. You may or you may not. All right. So that is it for this discussion of calorimetry. I have now been talking for nearly 2 hours. My throat is starting to let me know that that's what I've been doing. So I'm going to call it a night. We will finish Chapter 8 next weekend. I will see you around.